Okay.
Can you see my screen?
Yes.
Okay. Alright, so this is question 9, and the function for it is x squared minus 6x. So since there's no c, is x squared minus 6x plus 0. Now to find the vertex, I use the formula negative b over 2a. So over here, I'm about to find the x vertex, which is 6 over 2 times 1, because the a is 1, 6 is negative, but negative plus negative, that give a positive. That's why it's 6 over 2 times 1. So it's 6 over 2, which is 3. Now I'm going to find the y vertex. So what I'm going to do is to replace the x to 3. So I'm going to substitute, since now I know what's 3. So it will be 3 squared minus 6 times 3 plus 0, which give me 9 minus 18, which is equals negative 9. So my minimum value of the vertex will be 3, negative 9. So to find my y and x intercept, I'll just substitute 0 to the x. So that's 0, 0, which is the y-intercept, because whatever the y-intercepts is always gonna be 0. Y-intercepts is when x is equal to 0. My bad, sorry. So to find my x-intercept is when y equals 0. But this is a little bit difficult. It's not like you're only substituting 0 and everywhere. So x squared minus 6x plus 0. So I personally use the quadratic function to find my x intercepts. So I use the quadratic formula, which is right here in the corner. And then I substituted the values for the b and the a's, and then I ended up with 6, 0. And here's the scratch of the graph. The vertex was 3, negative 9, 3, negative 9. The y-intercepts was 0, 0, and the x-intercepts is 6, 0.
6, 0 and 0, 0, right? Because you have
Yes,
choice value.
0, 0. Yeah.
Right. Okay, great. I just want to, can you go up a little bit?
Yeah.
Beautiful work. But I just want to mention 2 things, make 2 comments.
Okay.
Right, so for the vertex, you have x value, you have y value, right? Maybe let's write down vertex x equals to here, then y equals to, all right?
Okay.
Okay, great. So that's
All
the vertex and the right quadratic formula. Great, good job, beautiful job. Thank you.
Thank you. Yeah.
So
How to stop sharing?
Andy wants to show 13. Let me make you a presenter, Andy.
Professor.
Yes.
I have a question. Are we all presenting today?
No, only if when you are ready, when you feel ready.
How many times do we got to present?
Yeah, because you present to get a presentation credit, right? You don't have to present every class.
Oh, okay.
No, you don't have to.
Mm.
Okay, and
No, she's asking how many times do we have to present?
How many times? Let's see. So we're up to homework 4 now, right? So I would say at least, try 2 of them. All right. If let's say in total, if we have 20 homework, try to present at least 10. All right, Andy. Let's see. After Andy, Jeremy, James, Lisbeth, Anna. Okay, Lisbeth, you're ready? If you're ready, go ahead. Let me make you presenters. So Anna. Yes, Ola. James. You know, by presenting, one way is to get your credits, another way is help us to review the material we have learned. Lisbeth is okay.
Okay, I'm sorry.
Okay.
So I'm going to be presenting number 11. You can see my screen, right? Oh, Jesus. Jesus. Can you see my screen?
Yeah.
Okay. So the steps were to find a vertex, y, x-intercept, and then sketch the graph. So for number 11, I found the vertex first. I found each number for the variables. For example, a equals 2, b equals 6, and then c equals 0. In order to find the vertex, I use the formula, which is b divided by negative 2a, or negative b divided by 2a, which I then substituted the numbers, and it was 6 divided by 2 multiplied by 2, and it gave me negative 1.5. That's for the x, and then I substituted that into the equation again. So negative 1.5 substituted into the x of the regular function. Sorry. And so then I just solved for it, and it gave me negative 4.5. So altogether is negative 1.5, comma negative 4.5, and that's the vertex. In order to find the y-intercept, is the x value is always 0, and the c value here was 0, so the y-intercept is 0, comma 0. For the x-intercept, I also used the quadratic formula, but I didn't show the steps. I did it like all at once in the calculator, and then I just put the numbers here, and it was 0, 0 and negative 3, 0. And then I just sketched the graph here, and as we can see, it's a little bit small, so that's why it looks like it looks like a parabola like that, but it is a parabola. Here's the vertex, here are the roots, and then the y-intercept as well. That's it.
Okay, great. All right, so one way you could use a quadratic formula, or you see this, you can factor out 2x.
Yeah.
You factor out 2x. Let me write it in the chat. So
I found the quadratic formula easier because I have used it before, so I just used it.
Okay, look this one in the chat.
Okay.
So the two terms both have 2x as common factor, right?
Mm-hmm.
So factor out 2x. Then what's left? X left for the first term, 3 left for the second term. Then we use zero property. So that means 2x is 0, can be 0, or x plus 3 can be 0. Of that, we get x equals 0 and x equals negative 3. So this is just another way of doing it. But this is beautiful work. Great.
Okay.
All right. Thank you.
Okay.
Okay. Andy, do you know how to show it? Okay. Okay, great. Who's this?
Lola.
Lola, great. Lola, go ahead.
I'll make it bigger. I don't know. Sort of.
I don't know. We can make it bigger ourselves.
Oh, okay. Then if you need help, you can make it bigger. Thank you.
You're welcome.
So I'm doing question 22, like 2.7, question 22. So the question is, assume the f is a 1-to-1 function. So what I did for question 22a, so if f of 5 equals 18, find f to the power of -1 of 18. So basically, what I realized is that so first you have to try to figure out like what is the inverse of f of 5 equals 18. So to find the inverse, we know that for everyone one-to-one function, f of x equals y, the inverse is going to be f to the power of -1 of y equals x. So if we do the same thing to f of 5 equals 18, the inverse is going to be f of -1 of 18, f to the power of -1 of 18 equals 5, which is the inverse of the equation we had earlier. So
Great.
for A. And then B, if f to the power of -1 of 4 equals 2, find f of 2. So if we do the same thing we did here, but this time we're turning from the inverse to the normal function. So I don't know if it's normal function, but yeah, I put it like that.
That's a function. Just a function.
I just said normal function, but yeah, something like that.
Or you may see one-to-one function because only one-to-one function has inverse.
Yeah.
Okay.
Okay. Yeah.
Okay, Lola.
Like she said.
We read this f raised by inverse, f raised by -1 to the inverse of f.
Okay.
Inverse of f. Inverse function of f.
So you say inverse of f.
That's right. Okay, great.
So we do the same thing, and then we find f of 2. If we change this, it turns into f of 2 equals 4, which is again the inverse. Yeah.
The inverse of the inverse. Yeah. Okay, good job. Let's see now. Andy, you ready? Okay, whoever is ready, all right, just share your screen with us. Okay, yeah, any of you is ready, just share your screen with us, then.
Am I the presenter?
Oh, I haven't yet, sorry. Oh, I did. You are present.
Okay.
Mm. Okay,
Can
Andy.
you see it?
Oh,
Can you
not
see
yet.
it?
Yes, now.
Okay. So I did question 2, and it asks is the quadratic function f of x equals to a parentheses h x minus h squared plus k is in standard form, and it's to like basically fill in the blanks, and yeah, that's what I did for A, B, and C of 2.
Okay. Can you tell us what you did, A, B, C?
Okay. So for A, I wrote the graph of f is a parabola with vertex, and I wrote x and y.
Oh no, hold on a second. Let me read in the chat. All right. So the function, one of the standard form we write as this: equals f of x equals a times x minus h squared plus k.
Okay.
Can you look in
Yeah.
the chat? Right. So this is one of the standard form, right? We call vertex form.
Yes.
So in here we have a, we have x, we have h, we have k.
Okay.
Which two makes a vertex?
Is it HK?
Yeah, h comma k makes a vertex. So your answer for A should be
H and K.
h comma k in the standard form.
K. Okay.
Right, makes sense? Let me see. If I
Yes.
give an example, f of x equals to 2, times x minus 3 squared plus 6. Can you tell me what's the vertex for this function?
That would be 3 and 6.
3 and 6, right? Okay.
Yes.
What if I write another function? F of x equals to x plus 2 squared minus 5. What about in this case?
Well, -5 is like the exponent. So is it like?
Oh,
two?
no, I'm sorry. I'm missing 2, missing square there. That should be x raised by square. Sorry. F of x equals to x plus 2 square. I mean, minus 5.
Okay, so that would be -2 and -5.
Great. Good job. Great. All right. Go ahead. Explain to us B.
So B, if A is more than 0, the graph of f opens blank, and I put upward.
Right.
And the vertex is a minimum.
Right.
In this case, f of h equals k is the minimum value of f. That's B.
Great. Okay. Yes.
And for C, if a is less than 0, the graph of f opens downward. In this case, f of h equals k is the maximum value of f. And that's
Great.
2.
Okay. Yeah. Okay. Beautiful work. Okay. Thank you. So that's Jeremy. Who's the next one? Whoever is ready, all right? Let's see what we have. Okay, Andy, you ready? Okay, Andy, you want to show 13, right? Are you ready? James wants to show 3.
Sure, but Andy's going first, so I'll let him go first.
Whoever is ready can go first.
Hello, can you hear me?
Yeah. Well, we can
So,
hear you.
I click the arrow, right? And then
Right.
share application screen,
That's right.
then share audio, and it says share, but I can press it.
Okay, you see your share application slash screen, right?
Mm-hmm.
Then they give you 3 choice.
Yeah.
Your entire screen or the second one. Choose the second one. Application window. Then click on your homework.
Okay.
Do you see your homework?
Yeah.
Great.
Does it show?
Yes.
Okay, so my exercise is number 13. It's f of x equals fx squared plus 4x plus 3. So to write it on standard form, you use the completing square formula, which is b divided by 2 to the power of 2. So it's 4 divided by 2 to square. It's 4. So you add 4 and subtract 4. Can you see my mouse?
Yes.
Okay. So you add 4 and subtract 4, and then you factor it. I mean, you put on the standard form, and so it's x plus 2 squared, which represents the parentheses of x squared plus 4x plus 4, and then minus 1 because of 3 minus 4. And then the vertex is minus 2 and comma -1 because of the HK form. To find the x-intercept, you let f of x represent 0, and here you factor x plus 1. No, wait. You factor, right? X plus 1 and x plus 3 for x squared plus 4x plus 3, right?
Right.
That gives you -1 equals x. And you substitute x with -1, and that gives you 0. So the x-intercepts are -1 and 0. For y, you let x equal 0. So x plus 4 times 0 plus 3. And that gives you 3 as y-intercept. And all the way at the bottom is the graph.
Okay, so Kaya, you have 2 zeros, right?
One for the y-intercept and the other for the x-intercept.
How many x-intercepts do you have?
2.
2, right? But here you only show 1. Which 2?
The one to the right.
You see here you have x plus 1 times x plus 3 equals 0, right? This should give you 2 solutions.
I see.
So which 2? So you have x plus 1 times x plus 3 equals
When you substitute x with -1,
you get 0, right?
yeah,
What about when you substitute x equal to -3?
it's +3.
So if x is a -1, you get 0. So the equation is true. If x is a -3, -3 plus 3,
For solving for x-intercept,
right? You have 2 x-intercepts, right?
yeah.
You only wrote 1. You only wrote x equals to -1. You're missing another one.
Oh, the -3 one.
Right, the -3.
I didn't write it there, sorry.
Right, it's okay. So that's why you see here your graph, right? You have -3 for one x-intercept. You have -1, another one x-intercept. Make sense?
Yeah, I didn't put it
Okay.
there.
Okay, great. Thank you.
You're welcome.
Okay, thank you, Andy. Okay, who's next one?
Me, Professor. Professor, can you hear me?
Yeah, I can hear you.
Okay, so for number 3, it's going to be another complete the sentence. So yeah. So for number 3, the graph of f of x equals 2 times x minus 3 square plus 5 is a parabola that opens upwards with its vertex at 3, 5, and f of 3 is equal to 5 is the minimum value of f.
Great.
So yeah, that's about it.
Okay, great. Thank you.
You're welcome.
Okay, let's see. Anybody else? Oh, Anna, right. Anna, have you, I made, right, you're a presenter. I made you a presenter already. You can go ahead. Today we're going to talk about polynomial functions.
Can you hear me, Professor?
Yes.
So this is for question 3, question 21. I follow the order of operations, so I start with G parenthesis 0, and then I apply the rule, the function rule here to evaluate. So then 2 minus 0 squared is equal to, then I start with the F, that F2 with the result here. So then 3 times 2 minus 5, that's equal 1. So A is 1. So in B, I did the same thing, follow the order of operation, and the result is negative 23. And that's it.
Okay, great. The only thing, great. So we just substitute, right? Okay.
Yes.
So A equals to A parentheses equals to 1 does not make sense, right? Let's write F of G of 0. F of G of 0 equals to 1, right?
Yes.
Yeah. Okay, B, let's write G of F of 0 equals to negative 23.
Okay.
Okay, so basically this is the composition of functions. Okay, great, Anna, thank you. Anybody else? Oh, Samir, let me make you a presenter, Samir.
Okay.
Yeah.
I'm gonna find the file first.
Okay. Anybody else wants to present today? Okay, otherwise I'm going to talk about the polynomial after Samir's presentation. You see, presentation could be very easy. Or Natalie. Okay, Natalie, get your stuff ready. Natalie, let me make a presenter. Yeah, get yourself ready. You know, if you like to present, get your files ready, load it up. Yes, Samir, we see your work. Go ahead.
Okay, so for 20 for 21, so basically here we have to use the function f of x plus 3x minus 5 and dx of 2x squared minus x
Hold on
squared
one
to
second.
evaluate the expression.
No, don't talk about 21. Talk about another question, because we just showed 21, right?
Yeah.
Yeah, we just showed 21. So can you show maybe 22?
Oh yeah, sure.
Okay, thank
So
you.
we use the function that's given to us to evaluate the expression. So here we have we evaluate the 4 for x, and here we evaluate 3 for g. So what I did first was I put the 4, evaluate the 4 for x, place that for x, and I solve the function. So for example, I did 3 times 4 minus 5, and then here we get 7. And then for g of x, I replaced that one with 3. So same thing what we did at the top here. We do 2 minus 3 squared, and we arrive with our solution here is negative 7. That's how you find your 2 points.
Okay, so that's f of 4 and g of 3, right? But
Yes.
look at your question. Look at your question. Look at wait. A, you have to find f of f4,
Yes.
right? So now you find f of 4 is 7.
Mm-hmm.
So you need to find f of 7. So this is composition of functions. You compose f with itself. Do you see that? You see f of 4 equals to 7.
Yes.
So now you need to substitute this 7 into this f of 4 for the question.
Okay.
So f of 4 now becomes f of 7.
7. Oh, okay.
Right.
And then from there I solve.
Right. From there, you just substitute into a function of f. Right. So f of 7. So think
F of
about
7.
7. 3 times 7 minus 5, which is?
So that means 3 times 4 is 21. Minus 5. That'd be like 19 or?
No, 3 times 7, 21. You have to take a
Oh,
5.
21. Then 21 minus 5 would be like 16.
16.
Yes.
Great.
Okay.
So f of 4 is 16. All right.
Yes.
Can you fix b?
And then for g, I substitute that for negative 7.
Right. Because the g of 3 is negative 7 now.
Okay. That means 2 minus, well, then I have to substitute that number, negative 7, for 3. That means...
No. You use g. You use function g.
Yeah, g for negative 7, right?
Right. Negative 7 squared, right? Negative 7, you square it.
Okay. Okay.
What's negative 7 squared?
Negative 7, negative 7 squared?
Yeah. Think about the negative 7 times negative 7. With negative
49.
Negative.
Isn't it 49?
Yeah.
Okay.
49. All right. So now you have 2 minus 49. So what should be your answer?
47.
47 positive or negative?
Negative.
Are you sure?
No. Just positive.
Which one?
49 minus 2?
No, not 49 minus 2. You have 2 minus 49.
Oh, 2 minus 49.
Right.
That has to be negative.
Right. So
Yeah, because
negative.
you're subtracting a small number with a bigger number, so it's gonna stay as negative.
Right. So your final answer should be for B, negative 47, right?
Negative 47.
Okay. All right.
So
Okay.
the only thing I need to do is just substitute those two numbers and that's it.
That's right. You need to do one more step because you only finished the inner one, the inner function. But this is
Okay.
composition of two functions. Function compose with itself. Make sense?
Yes.
Okay. All right. All right. Thank you.
You're welcome.
Natalie.
Can you see?
Yeah.
Okay, I'm doing question 27. This one. I hope nobody did it yet.
No, nobody did yet.
Okay, so the question was to show that f inverse equals g. So first we have to find the inverse of y of f. So we replace this with y. So y equals 2x minus 5. And then to make y the subject, I added 5 on both sides. And then it's canceled out. And then I had 2x. Y plus 5 equals 2x. And then I divided by 2 here. And then y became the subject. X became the subject, sorry. X equals y plus 5 over 2. And then I interchanged it, y and then x. So f inverse of x equals x plus 5 over 2, which is equal to g.
for x, then change the notation. Okay, thank you, Natalie. That's great. Anybody have any questions? Okay, I'm going to talk about polynomials, all right, today. There's videos in there under the content, so you may watch about polynomials. So first, I'd like you to remember this standard form for polynomial. Right here. So a polynomial, you can think this P as f, all right, f of x equals to some number multiplied by x to the nth power, then plus some other number multiplied by n minus 1 power, so on and so forth. You can think this is an x squared term, this is an x term, this is a constant term, right? We know three kinds of polynomial function already. Let's see, f of x equals to 5. Maybe let me make another function, g of x equals 3x minus 2. H of x equals to 2x squared minus x plus 4. So these three kinds of polynomial functions we know already. The first one is polynomial with 0 degree, because that's x raised by 0, because 5 is, we can think as x raised by 0 equals 1. 1 times 5, still 5. So this is a 0 degree polynomial. And then the second one, g, is a linear function. It's a first degree polynomial. Then the third one is a quadratic function. It's a second degree of polynomial. So we know these three kinds of polynomial function already. And the exponent of x can go higher. These two can be 3, 4, 5. Then we just call polynomial of degree n. Let me make another example. Let's say I have another function, k of x equals to negative x raised by maybe 7 minus x plus 9. I can make an example of, see, x raised by 7. So this means this is called degree 7 polynomial. Degree 7 polynomial. So the highest exponent of the variable is the degree of the polynomial. All right. And the leading term is important, right? So anxn. The term has the highest power. It's a leading term. Sometimes it may not be written in order. So looking for x has the highest power. You see, the first one is a 0 degree polynomial. The second one, x raised by the first power. Then x raised by the second power, x raised by 7th power. So those are leading terms. And those guys are called the leading terms. All right, 3x here is a leading term. A constant function, just a number. If we see this one, let's write down. So this is the f of x equals, oops. No, I don't need this. I want this. So the f of x equals to, right? So this is a function. So this function is 3x raised by 5 plus 6x raised by 4, 2x raised by 3 plus x squared plus 7x minus 6. Minus 6 is a constant term. And the highest term is x raised by 5. So we call 3x leading term. 3x raised by 5 is called the leading term. And 3 before the variable is called the leading coefficient. Right? So this is a 5th power. So it's a polynomial of degree 5. All right. Right. Okay. Degree 0, constant function degree 0, linear function degree 1, quadratic function degree 2, cubic function degree 3, so on and so forth. So let's see some basic graphs. So this is a linear function, y equals to y equals to x, or f of x equals to x, right? Better to use our language because we're in a function world. Let's call this f of x. So f of x equals to x. We call this identity function. Identity function. Y equals to x squared, or f of x equals to x squared. Quadratic function. F of x equals x cubed. Cubic function. F of x equals x raised by 4. You know, it looks like a parabola, right? But it is a little bit chubbier for parabola than parabola. Then f of x equals x raised by 5. You see x raised by 5. Let's see the trend. Let's see the trend, right? We see when the leading coefficient is odd degree, or when the polynomial with odd degree, you see the first one is odd degree, right? Let's see, degree 1. The third one, degree 3. The last one, degree 5. You see, when the polynomial, excuse me, when the polynomial has odd degree and the leading term is positive, right? X raised by 5 positive, x raised by 3 positive, because the leading coefficient is 1. It's 1. So positive term, when the leading term is positive and the degree is odd, you see the trend going from take the first quadrant and the third quadrant. First quadrant and third quadrant. A little bit wiggly. You know, increase the degree, more wiggly, right? But still in the first quadrant and the third quadrant. No, even degree. Let's see the even degree. So this is degree 2. This one degree 4. You know, we can draw more. We can draw degree 6, degree 8. They all have this kind of shape. They take the first quadrant and second quadrant. And when the leading term is positive, they all go upwards like this. They all go upwards like this. It's when the degree increases more chubby. You see this one too, right? So this is a trend. This is a trend for polynomial functions. So let's see the first one. Let's see example 1. So p of x equals to negative x cubed. Well, x cubed is this one. Now we just negate all the y values. So the negative y values here is being moved upward. It's being moved here. Right? Think about negative 1 will be positive 1, because negative 1 will be positive 1. And positive, guys, when we put a negative sign in front of it, it becomes negative. So we will have a graph like this. So negative x cubed becomes like this. We'll have here, down here. Negative, it doesn't really give us. But just follow my arrow, okay? Negative x cubed just becomes a graph of this. Becomes this part and this part stay or doesn't stay. All right, so basically this branch goes upward and this branch comes downward because we put a negative sign in front of it. Now let's see B. X minus 2 raised by 4. Well, raised by 4, we know we have this kind of shape. Right? We have this kind of shape. Now, every x value is being shifted to the right. So this minus sign is saying x value shifted to the right. So 0 point is being shifted to 2. And we will have a graph here. So basically, this graph be moved. Remember, we talked about transformation. It be moved here. That's x minus 2 raised by 4. X minus 2 raised by 4. So it's important to remember those basic graphs. And all other graphs is just transformation of them. Let's see this one. Negative 2x raised by 5 plus 4. X raised by 5. We have x raised by 5 here. So basic graph looks like this. Now, we multiply with negate. Let's negate first. So negation, put this branch going upward. Okay? And put this branch going downward. Then multiply by 2. Every y value is being increased by 2. That means this becomes skinnier. Because 1 here before now becomes 2. 4 there before now becomes 8. Right? So the graph becomes a little bit skinnier, sharper. Then add 4. Every y value is being lifted up 4. So then this graph 0 being lifted up to 4. So the graph looks like this. Let's see, maybe we'll have down here. Oh, okay, right here. We have p of x equals negative x cubed, right? Becomes this one, negative x cubed. Then this is x minus 2 raised by 4. Okay, we shifted the x raised by 4 2 units to the right. And now this becomes negative 2x raised by 5 plus 4, right? X raised by 5 is what this, now being flipped like this. Now double it, right? Multiply by 2. Then every y lift up 4 units. So basically look at the 0. 0 here before, now become 4. 0 become a 4. So transformation of these basic functions. So those are the basic graphs for polynomials. As you can imagine, you know, if the leading term is x raised by 7, it goes more chubbier. If degree 6, more chubbier, so on and so forth. Any questions? Okay, so with polynomial functions, we talk about end behavior and leading term. Leading term, this is the leading term. Right? In here, leading term is x raised by 4. Here, leading term is negative 2, x raised by 5. And also, end behavior, we're considering this. End behavior for this one. This goes down to negative infinity. This goes up to positive infinity. Similarly, this goes up to positive infinity. This goes up to positive infinity. And also same for this. This side goes up to positive infinity. This side goes downward to negative infinity. This is end behavior. So x goes to infinity means x becomes large in a positive direction. X goes to negative infinity means x becomes large in the negative direction. So it means x becomes smaller and smaller. X becomes bigger and bigger. Same thing for y. A polynomial function has r degree if x approaches to positive infinity y goes to the negative infinity, we have this kind of behavior and behavior. And this is the first one. See, if x goes to negative infinity, right? X value is equals this way, becomes smaller and smaller. Y value becomes smaller and smaller. Right? This one is seeing x become larger and larger, bigger and bigger, but the y value goes down, becomes smaller and smaller. And this end behavior is seeing x becomes smaller and smaller because we're going this way, right? And the y becomes bigger and bigger. X becomes bigger and bigger, y becomes bigger and bigger. X becomes smaller and smaller, y becomes smaller and smaller. X becomes bigger and bigger, y becomes smaller and smaller. So this is with leading coefficient negative, right? And it's an even degree. So those are in behavior. Okay, if a polynomial has r degree with leading coefficient positive, we always have this kind of shape. Goes from first quadrant to the third quadrant. If leading term is negative, going from second quadrant to the fourth quadrant, we have this kind of shape. Polynomial degree with even degree, we have this W looking. You know, raise your two hands. It's upward, upward, upward. With positive, with leading coefficient positive, we have upward and behavior. If the leading term is negative, we have downward and behavior. All right. So those are some trends for polynomial functions. Let's see this one. Polynomial of p of x. We'll use p for polynomial. Negative 2x raised by 4 plus 5x raised by 3 plus 4x minus 7. So this is a degree 4 polynomial, right? Degree 4 polynomial. And then we have negative. It's negative, so we know it's downward this. The end behavior is downward. And then it's a 4th degree. 4th degree means the graph wiggles 3 times. All right. 4th degree means the graph wiggles 3 times at most. So you see we have this first wiggle, second wiggle, third wiggle. Right, we can graph some points. It's difficult to use hand to graph, but for us, so we know, okay, the leading term is negative, we know the end behavior goes down, both sides goes down. And the polynomial degree 4, we know it looks like a W, wiggles in the middle. And then this negative 7 is 0, comma negative 7 is a y-intercept, right? Because x equals 0, those terms are gone, we'll get negative 7. So 0, negative 7 is a y-intercept. And for x-intercept, we go through the same process, but usually it's difficult to find for higher polynomials, zeros. So, right, we determine the end behavior, right? Because it's a 4th degree, leading term is negative, so we have this kind of end behavior. Let's say another one. So this is degree 5 polynomial, and it's positive, right? Degree 5, we know is odd, goes from first quadrant to third quadrant, right? You see the graph. Do we have the graph? Yeah, so basically like this, right? Because the coefficient, because the degree is odd, coefficient is the first leading term is positive, so have a graph from the first quadrant to the third quadrant. So the end behavior is this. Okay, I'm not going to talk about the higher zeros for higher degree or the x-intercepts for higher degree polynomials. For us, if we know the end behavior degree, to be able to recognize the polynomial of degree, right? give us any polynomial, we're able to tell the degree by the leading term or the end behavior at this moment, that's good enough. So that's all for polynomials. Let's see. Let me assign you some homework. Okay, I'm going to ask you to sketch some graph. All right. This is 6, 7, 8. So I'm going to talk a couple of them as a review of transformation of functions. So let's see homework 5. So I want you to do, I'm going to show 5. All right, I'm going to talk about 5. For you, I want you to do 6, 7, 8. So this is homework 6, 7, 8. So homework 5, 3.2, 6, 7, 8. For now, okay, I'm going to add more later. Let me talk about 5. Let me talk about 5. Let's say A, right? A, first we look at the x squared. Well, we know how to graph x squared. That's just a polynomial. That's just a quadratic function goes through the origin, right? Now minus 4. Minus 4 here means every y value being lowered 4 units. So that graph would be, I'm going back to this one. I want you to be able to use this reference graph. Okay, remember we have this reference graph. X squared minus 4 would be negative 4. Let's see negative 4 is somewhere here. But basically just push down this graph 4 units. 4 units down. That would be x squared minus 4. So remember we're using transformational functions. Okay, let's see B. Bx minus 4 squared. You see here, the square is outside. So x minus 4, that means x value being changed. X value being changed. So that means the graph was here before. Oops. Oh, nice. Okay. Was here before. Let's say this is the x squared graph, right? Now every x value being changed to where? Being pushed 4 units to the right because it's a negative sign. So x minus 4, let's see if this is a 4.4, x minus 4 will be here now. Okay, so here, imagine this is a 0, 0, the origin point. It's being pushed to the right 4 units. So this is x minus 4 parentheses squared. So that's B. Well, let's see C. 2x squared minus 2. Now x squared, every y value for x squared be multiplied by 2. So the graph like this before now becomes skinnier. Because imagine before, if x equals 1, x squared is still 1. But now it be multiplied by 2. So it becomes 1 and 2. So the graph is being stretched. It's being stretched longer. Now minus 2. Minus 2 means every y value being shifted 2 units down. So the graph looks like this now. It becomes skinnier and being pushed down 2 units. What about D? D now, x being pushed 2 units to the right, and every y value is being stretched by scalar 2. So that means that looks like this graph now be moved 2 units, or actually let me just delete this one. So I'm talking about D. Okay, I'm talking about D now. So x 0 point now becomes 2.0, and every y value being stretched to, because before was 1, now becomes 1, 2, right? So the graph is being stretched longer and being pushed to the right 2 units, because the x value is being reduced by 2 units. So minus sign indicates pushed to the right. If it's a plus sign, it means push it to the left. All right, so I want you to try 6, 7, 8. So this is all about polynomials. Don't worry about the rest. So only 3.1, 3.2. We only cover these two, 3.1 and 3.2. All right, so we're going to talk about rational functions today. That's it for polynomial functions. Okay, rational function 3.7. We skip 3.3, 3.4, 3.5. 3.7 rational functions. I also loaded one video in the under the content in CUNY Blackboard. So watch the video, talk about rational functions, talk about asymptotes. All right, asymptotes. So what is a rational function? A rational function is a fraction. The numerator is a polynomial function. The denominator is also a polynomial function. Because x appears in the denominator, so it gets the name rational functions. Okay, this is the basic function, rational function, 1 over x. 1 over x. Let's see if we have a graph here. Oh, right here. So memorize f of x equals 1 over x as this graph, right? So one piece is in the first quadrant, another piece in the third quadrant. So that's a 1 over x graph. What's the end behavior? As x approaches to 0, y value shoots to infinity, right? Can you think about the x? If x becomes smaller, 1 divided by a smaller number becomes bigger. But if x goes bigger, if x goes this way, becomes bigger and bigger, the y value goes smaller and smaller. Right? Approaches to 0, but it will never be 0. And in the third quadrant also, because if x is a negative value, we get a branch of this graph. All right? So 1 over x has 2 pieces of graph. So it's discontinuous at 0, 0. One graph like this goes on forever. This from this side goes on forever. This is end behavior. And when x is a negative value, goes on forever. It goes on forever. Okay, so that's the graph of f of x equals 1 over x. Let's see some. So let's see what do we care about rational functions. Let's see in this case, we see 1 over x, and x cannot be 0, right? Let's consider the domain of this function. Domain is x is not 0, right? X cannot be 0. That's the domain. So what this becomes? This becomes an asymptote. So the y-axis becomes asymptote. Asymptote means the value of x is not in the domain of the function. We use these asymptotes to represent. Let's see in this case. We will say A, if A is not in the domain, is a vertical asymptote. Here creates a vertical asymptote. It creates a vertical asymptote. We use this dotted line to represent. Let's say here, if B is not in the range, of the function, we use horizontal dotted line. And this is called horizontal asymptote. Okay, transformation of f of x equals 1 over x. Right? We have ax plus b over cx plus d, like two functions here. R of x equals 2 divided by x minus 3. So let's think about this one, right? Transformation of functions. X value is being pushed 3 units to the right, right? You see x value, imagine our original function is here, right? Two pieces of graph was here. Now x value being pushed, x minus 3 being pushed 3 units to the right. That also means this origin, the origin being pushed 3 units to the right. And then the function is multiplied by 2, right? The scalar, we have scale of 2, just like this. You think about f of x equals 1 over x. We can rewrite r of x as 2 times 1 over x minus 3. And then 2 times f of x minus 3, right? Because the input, think about f of x is 1 over x. Then f of x minus 3 is 1 over x minus 3. So you see R is a transformation of F. It's a transformation of F. Okay, so make sure you understand this example. You know, once we remember the graph of 1 over x, and we can figure out it's a transformation, another function is a transformation of this function, and we can use the basic graph, and we call reference graph. You can use this graph, reference graph, to graph the transformation of this graph. Let's see more example. Okay. Any questions with this example? This is a very important example. So to see R of x is a transformation of 1 over x. Okay, similarly, let's see B, S of x. And B, we can write as 3x plus 6 minus 1, right? So we can change 5 to be, let me see if they show the steps. Okay, they didn't show the steps. So let me show the steps here. So we can rewrite this function as the top, the numerator as 3x plus 6 minus 1, because the 6 minus 1 is still 3x plus 5. So I can write this function as 3x plus 6 minus 1 divided by x plus 2. Now, 3x plus 6 divided by x plus 2 gives me 2, right? Or gives me 3. So now I can rewrite as 3 minus 1 over x plus 2. So that's here. That's how we get this. All right. So first, we change 3x plus 5 as 3x plus 6 minus 1. Then 3x plus 6 divided by x plus 2. You just factor out 3, right? I factor out 3. That becomes 3 multiplied by x plus 2. Then x plus 2 divided by x plus 2 becomes 1. So this function s of x can be rewritten as 3 minus 1 over x plus 2. Now, negative 1 over x plus 2. We can think as a transformation of f of x. F of x is 1 over x, right? So we can think this is a negative f, and the input is x plus 2. Because f of x plus 2, that's 1 over x plus 2. Then put a negative sign. Put a negative sign. Right? That becomes negative 1 over x plus 2. Then 3 here, or we can write here, add 3. And now we can think, now we know the graph of this. Now we can graph this. But x is being pushed to the left 2 units because we have x plus 2. Plus means push the graph left 2 units. So 0, 0 here before, right? Before 1 over x, we have this piece, we have this piece. Now, x plus 2 means we push this 2 units, 2 units to the right. It was here before, it was here before. Now being pushed 2 units to the right. And then we have this negation sign. Negation sign. Every y value is being negated. So this piece comes down, that piece comes up. Then so pushed 2 units to the right, to the left, and being negated is a flip, is a reflection. So this piece being reflected to be this piece, and this piece being reflected down to x-axis. Then we have this add 3 in the end. So every y value being pushed, so the graph being pushed 3 units up. Okay, it was here before, it was even down here before, it's been pushed 3 units up. All right. So you see this one being pushed 3 units up, this one flip over, being pushed 3 units up. And the other trick is to be able to write one function in terms of another. You see here, we're writing s of x in terms of f function. F of x is 1 over x, and f of x plus 2 is 1 over x plus 2. Okay, any questions? This might be a little bit confusing in the beginning. Okay, let's see this one. This one may be even more complicated. So the function is a polynomial in the numerator, polynomial in the denominator. So numerator will have 2x squared minus 4x plus 5. Denominator will have x squared minus 2x plus 1. We can factor this, right? We write it as a form. So have this, the denominator we can write as x minus 1 squared. The numerator, we won't be able to factor the numerator. But from here, we see 1 is not in the domain, right? Because x minus 1 equals 0. X cannot be 1. That's the domain, right? X can be any other number, real number, but 1. Because 1 minus 1 causes 0 in the denominator. Because x cannot be 1, x equals to 1 is a line, is a vertical asymptote, creates a vertical asymptote. So we write it like this. X equals 1 creates a vertical asymptote. We write the vertical asymptote as a dotted line. And the graph will be on both sides, but the graph will never cross this vertical asymptote because 1 is not in the domain of the function. Okay, so that's vertical asymptotes. Let's figure out the vertical asymptote for this function. So we want to factor out the denominator. So factor out 2x minus 1, x plus 2. So then x, if x is a half, this will be 0. If x is negative 2, this will be 0. So we have 2 vertical asymptotes at x equals a half and x equals a negative 2. Right? If we graph, we have this. X equals a half, we draw a dotted line. X equals negative 2, we draw a dotted line. All right. We don't care about the rest of the graph yet. But for at this moment, we just want to see the domain, all right? So vertical asymptote comes from the domain. Domain. The domain for this function is x cannot be half and x cannot be -2. That's the domain. And when x equals to half, x equals to -2, that creates two asymptotes, vertical asymptotes. Okay, let's see how do we graph a rational function. So we want to factor the numerator, we want to factor the denominator. All right, let's see what, right, to factor the numerator, this one cannot be factored. So some numerators, some polynomials cannot be factored, but some of them can be factored. Let's say this one can be factored. 3x squared minus 2x minus 1 can be factored. Okay, how do we find? So this is to find vertical asymptote, right? Finding vertical asymptote is to find the domain. But how do we find the horizontal asymptotes? We use something called the ignore rule. So take the leading term. Only consider the leading term. So ignore the rest. So the horizontal asymptote comes from those two leading terms. So forget about the lower terms. Forget about lower terms. So 2x squared divided by 3x squared divided by 2x squared. X squared by x squared equals to 1. So we have 3/2. So that's the horizontal asymptote, 3/2. So when we graph it, we graph at the value y equals to 3/2. We graph dotted line. So that's horizontal asymptote. Okay, this is called ignore rule. Ignore the lower terms. Only take the leading term. Only take the leading term to get a horizontal asymptotes. Okay, at this moment, we only consider, so let me pick some homework. We only going to do to draw vertical asymptotes and horizontal asymptotes. So we'll talk about this next class. Okay, good. So I'm going to pick 21. So I have 6, 7, 8 before. Now let's do 21, 23, 25, 27, 29, 31 odd numbers. I'm going to add to the chat. So 6, 7, 8. Then this is a 3.7. 3.7, 21, 23, 25, 27, 29, 31. So 21 up to 31 odd number. Okay, those will be homework, but let's talk about this homework. I'm going to talk about those even numbers. Right? Let's figure out the vertical asymptote first. So vertical asymptotes, I look at the denominator. I have x squared minus 1. I said, okay, let me set that one to be 0. What happens? So x squared minus 1 equals to 0. I factor this, right? I can factor as x plus 1 and x minus 1. And then this equals 0, that means x equals -1 and 1. So I have two vertical asymptotes. So this gives me, so when the denominator is 0, that gives me vertical asymptotes. So how do I figure out horizontal asymptotes? Horizontal asymptotes by ignoring the lower terms. Only take the leading term. That's 2x over x squared. When I simplify, I get 2 over x. Well, 2 over x. 2 over x. What does this mean? How do I figure out the horizontal asymptote? X cannot be -1 and 1, right? But x can be as small as possible and as big as possible. If x is going to negative infinity, which means x is a very, very small number, I would get a very, very small number. If x is a very big number, no, if x is a very small negative number, I will get a very small number, right? Because negative, imagine 2 divided by negative 0.000001. I would get negative 2000000, many zeros, right? A very, very small number. It's a negative, a big negative number. So that means this whole thing goes to negative infinity. If x goes to positive infinity, 2 divided by a big positive infinity, big number, that will become a very small number, small positive number, right? So that's telling me I will not get horizontal asymptotes. I will not get a horizontal asymptotes. Let's see for this one. This one is similar, right? If we think about the horizontal asymptotes, we'll ignore the lower terms. We have 2x over x squared. Then we have 2 over x. Well, for 26 is different, right? We have ax squared divided by 4x squared. That's 2. So we do get a horizontal asymptote 2. So y equals to 2 is a horizontal asymptote for this function. Similarly, do the rest. All right. For this one, we get 5, right? Horizontal asymptote 5x cubed divided by x cubed. That's just 5. For this one, we get, simplify, we get x cubed divided by x squared, we get x. So we won't get horizontal asymptotes, but we get x. If a horizontal asymptote exists, it's a number. Well, vertical asymptotes, we consider the denominator, right, to be 0. So let's look at the 24. Will the denominator ever be 0? Right? This is quadratic. Now we can put into quadratic functions to see if this will ever be 0. Actually, we find out this denominator will never be 0. That means we will not have vertical asymptotes. Similarly, 26, we set the denominator to be 0, then we try to solve. We get 2x plus x minus 1 to be 0. Then we can factor. Right? When we factor, we get 2 values. But this is already put in a factor form. We just set this one to be 0. Then x equal to 3 would be one vertical asymptote. X equal to 4 will be another vertical asymptote. Similarly, we try to do for 30 and the 32, right? 32, we see the 2 vertical asymptotes are -2 and 2. Okay, so try 21, 23, 25, 27, 29, 31 as your homework. Also, with the previous from 3.2, 6, 7, 8. This will be your homework 5. I'm also going to put on the blackboard and content. All right. Okay. Any questions? Anybody has any questions? So today we talk about the polynomials, right? For polynomials, we need to know the degree of the polynomial or the end behavior of the polynomial. The degree of the polynomial gives us, if it's odd, we know the graph, right? From first quadrant to third quadrant, if the leading term is positive. From the second quadrant to fourth quadrant, if the leading term is negative. If degree even and the leading term is positive, we have upward. We have upward W-like. And if the leading term is negative, we have downward W-like graph. Then we talk about rational functions. Rational functions, the numerator is a polynomial, the denominator also polynomial. We talk about how to find the vertical asymptotes and horizontal asymptotes. Vertical asymptotes come from setting the denominator to be 0, then solve for x value. Horizontal asymptotes come from the leading terms. Ignore the lower terms in numerator. Ignore the lower terms in denominator. Only consider the leading term. If the leading term ends up to be a number, that's our horizontal asymptote. If then the leading term, the division of the two leading terms with x in it, that means we don't have horizontal asymptotes. All right, so try those homework, to practice those homework. All right, hopefully next time we'll start with reviewing this, and hopefully some of you can present. All right, and if you don't have any questions, I'll see you on Friday. Okay, thank you.